Hello, my name is Alvin Thamrin. I shall be your presenter on this topic, cloud-based blockchain for secure and reliable big data storage service in healthcare systems. This presentation shall mainly discuss the following topic. We start from the motivation and background to the definition of an electronic health record or EHR, the introduction of our approach, which is cloud-based blockchain and light blockchain, the block record types or transactions that can be found in our blocks, the structure of our proposed cloud-based blocks, role-based access control policy implemented as our access control mechanisms, encryption and decryption for data in the blockchain, the consensus process of our approach, case studies conducted, conclusions, and future work. There are many other studies that studies the possible integration of blockchain into the healthcare sector, mainly to create a system that would allow medical data to be stored and shared among doctors and patients across different hospitals in a more streamlined manner. However, many of these studies uses an off-chain storage approach to avoid storing EHRs in the blockchain to save space and to avoid scalability issues. EHRs are stored in a third-party storage outside of the blockchain, hence off-chain storage, while their metadata are stored in the blockchain. Our goal is to explore the possibility of storing EHRs in the blockchain to take advantage of the immutability, redundancy, and tamper resistance that the blockchain brings. What is an electronic health record? It can simply be defined as a medical information of a patient that is stored electronically in a digital format. An electronic health record, or EHR, can contain multiple forms of data. This ranges from data that can be represented in text format only to imagery and videos, such as X-rays, CT scans, ultrasound videos, and more. Note that EHRs are considered confidential as they contain patients' personal and private information. Thus, any storage medium that deals with EHRs must be kept secure from unauthorized access. We introduced cloud-based blockchain and the light blockchain as part of our approach to store EHRs in the blockchain. A cloud-based blockchain is a blockchain incorporated in the clouds. CBC, or cloud-based blockchains, stores all data including EHRs in multimedia file format. A light blockchain, LBC, is a blockchain incorporated by all regular peers in their local machines. LBC stores the same data as a CBC except for the multimedia files. As shown by this figure over here, a CBC and LBC shares the same blockchain length or height. They also have a one-to-one block similarities, where each corresponding block in a CBC is identical to a block in LBC, with again exceptions of multimedia files. This allows end users to retrieve any contents in a CBC via an LBC on their local machines. More specifically, regular peers can use the metadata stored in an LBC to request the corresponding multimedia files stored in the CBC somewhere in the clouds. There are three distinct types of participants or entities that are present in our blockchain network. These are regular peer agents, super peer agents, and cloud manager agents. Regular peer agents are software agents representing doctors, nurses, and patients who are the end users of the blockchain network. Super peer agents are software agents representing hospitals. Only one super peer agent per hospital is allowed in the network. The super peer agents also have the authority to create and vote on a new block by partaking on a consensus process with their fellow super peer agents. Cloud manager agents are software agents who maintain a private cloud owned by a hospital. As seen on the figure, regular peer agents and super peer agents manages a copy of a light blockchain or LBC in their local machine, while cloud manager agents manages a copy of the cloud blockchain or CBC. Regular peer agents communicate with their respective super peer agent and cloud manager agent to submit new records as well as to access data stored in the blockchains respectively. There are three types of block records that can be stored in a cloud-based or light block. These are user profile record, a set of access control policy record, and a medical record. A user profile record contains the user account information of a regular peer agent that participates in the network. A user profile record is created when a new participant joins the network or when an existing user profile is updated. Therefore, a regular peer agent may have multiple user profile records in the blockchain, but only the most recent one is valid. User profile record is defined as a 6-tuple with ID, name, private key, public key, secret key, and timestamp. Note that the private key and secret key is stored in ciphertext form, as they are encrypted by a super peer agent that represents the hospital that the user is associated with. Access control policy records contains a set of access control policies that must be followed by participants in the network. An access control policy record is created when a hospital establishes its access control policies or when the policies are updated. Therefore, each hospital may have multiple access control policy records in the blockchain, but only the most recent one is valid, similar to a user profile record. An access control policy is defined as a triple with set of policies, hospitals, and timestamp. A medical record contains the text-based medical reports of a patient and metadata of the associated multimedia files resulting from a doctor's visit, where we define a hospital visit as a patient visiting a hospital for any reason. A medical record is defined as a 6-tuple with identifications, hospitals, text-based data or TXD, metadata, timestamp, and index link. Note that the index link enables all medical records of a patient to be linked together as a singly linked list format. This allows an efficient information retrieval of the patient's medical records regardless of where they are stored in the blockchain, providing that the location of the latest medical record is known. This figure shows an example of the structure of a cloud-based block CBH+1, where H is the height of the blockchain. A cloud-based block consists of these three components, namely the regular component A, multimedia component B, and verification component C. Component A contains the previous block's hash value represented by hash CBH and hash LBH. It also contains the block's timestamp, ID, and current length H. Block records such as user profile, access control, and medical records are also stored in component A. Component B holds the actual multimedia files compressed together with their metadata recorded in component A. Component C contains the hash value of component A, represented by LBH+1, the hash value of component A and B, represented by hash CBH+1. It also contains a list of digital signatures of all super peer agents who have approved this block during the consensus process. Algorithm 1 shows how a new cloud-based block CBH+1 is generated by a super peer agent. The super peer agent creates an empty block first and fills it with initial information of timestamp, block ID, block length, and the previous block's hash value. If multimedia files are present, then the super peer agent would encrypt them first before compressing all of them into the component B of the block. Metadata such as offset values and file length are recorded and saved into each medical record associated with the multimedia files to allow future extraction of said file from the component B. Every block records given in the input list, as shown in step 7 to 15, is then encrypted to preserve the patient's privacy, except for access control policy records. Finally, the block's hash value is calculated and added to block's component C. A digital signature is also created based on said hash value and added to the digital signature list in component C. Note that the digital signatures from other super peer agents will be added to the digital signatures list during the consensus process. Additionally, a light block, LBH+1, can be created by simply copying this cloud-based block CBH+1 and removing its component B. Role-based access control policies are implemented to enforce what data that regular peers based on their credentials can access. A regular peer agent who represents an end user must seek permission from a super peer agent for access to sensitive data such as EHRs in a light blockchain or cloud-based blockchain. Since there are multiple hospitals in a blockchain network, each policy record is defined to be hospital-wide, and this means that a policy record that is applicable to a certain hospital may not be applicable to another one unless otherwise specified. Here we show examples of the policies that can be found in our proposed blockchain system. There are two types of policy types. An operation type specifies a permission or task that a regular peer is allowed to do, and the second one is a relationship type that specifies the relationship among multiple regular peers. Policy PL1 dictates that a peer with a patient role can access a patient's information only if the peer agent is requesting the peer's own information. So essentially, a patient accessing their own information. This policy involves only a single patient as stated by the role component. Policy PL2 Meanwhile, dictates a peer with a doctor role can access a patient's information only if the peer is recognized as a family doctor of the patient and if the peer is the current family doctor of the patient. This policy involves a single patient and a single doctor as stated in the role entry. Patient PL3 establishes the relationship between patient P and Dr. D in Hospital 1. Dr. D is recognized as a family doctor of patient P, and this relationship is a necessary requirement for other policies that involve Dr. D and patient P, such as policy PL2, as shown by one of the conditions that must be fulfilled. Policy PL4 establishes another type of relationship between Dr. D from Hospital 1 and patient P from Hospital 2. This policy establishes Dr. D as a referral doctor of patient P with a specified expiration date. This policy is considered invalid once time has passed the expiration date, and this in effect gives Dr. D temporary status as patient P's doctor. Every regular peer agent is assigned a pair of public and private keys stored in their user profile record. These keys are used to provide identification via digital signatures to other peers in the blockchain network. Every regular peer agent also possesses a symmetric secret key stored in their user profile record. This key is considered as a secret key used to encrypt and decrypt any data owned or generated from said peer. The secret key is encrypted by a super peer's agent's public key. A regular peer agent must make a request to its super peer agent for the permission to unlock and use this key. Note that this secret key is only handled by the software agent and shall never be presented to any end user for security reasons. And this figure shows the procedure involving a doctor wanting to retrieve their patient's information from the blockchain. The doctor is represented by regular peer agent 1 and the patient by regular peer agent 2. The procedure starts with regular peer agent 1 sending a request to super peer agent A, which represents hospital A. The super peer agent A then checks its access control policies to decide whether or not to grant permission to such requests. If permission is granted, then the super peer agent retrieves regular peer agent's secret key from their user profile record and reconfigures it by decrypting and re-encrypting the key with the regular peer agent's 1's public key before passing it back to agent 1. Regular peer agent 1 will then decrypt the key using its private key, thus giving the user, the doctor, access of the patient's text-based data or EHRs that are stored in the Light blockchain. As shown on the figure, if the doctor wishes to access or retrieve multimedia files that are only present in a CBC, then additional steps must be followed. The procedure involves similar requests to the super peer agent A, but this time involving Cloud Manager A. The Cloud Manager extracts the requested files and returns the link back to Agent 1, and Agent 1 can then use this link to download the files where they can be decrypted using the previously received patient's key. The consensus process in our approach requires a majority approval from the super peer agents participating in the blockchain network. For a block to be approved, it must receive at least half or more approval from all other super peer agents participating in the network. This excludes the block announcer. The block announcer is defined as the super peer agent who initiates the consensus process by broadcasting a new cloud block and light block to the rest of the super peer agents. The block announcer can also be called as the primary super peer agent. This figure shows an example of the consensus process with three distinct hospital groups. The first group is consisted of the primary super peer agent, Cloud Manager Agent 0, and regular peer agent 0. The second group is consisted of super peer agent 1, Cloud Manager Agent 1, and regular peer agent 1. The third group is consisted of super peer agent 2, Cloud Manager Agent 2, and regular peer agent 2. The consensus process is divided into 5 phases, namely the initial verification, the block announcement, verification and approval, collection and verification, and notification. The initial verification phase involves the primary super peer agent creating a new cloud-based block and light block. The cloud block is sent to the Cloud Manager agent to ensure that the block is valid using the cloud's blockchain. The next phase involves the primary super peer announcing the newly created cloud and light block to all other super peer agents. The other superpeer agents would then proceed to download these blocks from the primary superpeer agent. During the verification and approval phase, superpeer agent 1 and 2 shall attempt to verify this cloud and light blocks using their own cloud manager agents. If no error is detected, then a digital signature is created based on the block's hash value and is then sent back to the primary superpeer agent. The primary superpeer agent waits until it has collected at least half or more valid digital signatures based on the number of superpeer participants in the network. And in this scenario, that would simply be 1. In this case, the primary superpeer agent would only need to wait for a minimum of 1 valid digital signatures aside from its own. Once enough signatures are collected, the list of digital signatures are then inserted to the block, and the block can finally be considered to be approved. The notification phase involves the dissemination of these digital signatures to other superpeer agents and cloud manager agents to complete their copy of the cloud and light blocks. Regular peer agents shall receive a completed light block from their superpeer agents directly. Now we present the case studies that have been conducted to test our approach effectiveness. The first case study involves finding an ideal size of cloud-based blocks, as large sizes of cloud-based blocks presents major challenges for maintaining cloud-based blockchains in the clouds. In this experiment, we generate dynamic number of blocks per day based on the number of patient visits to a simulated hospital during that day. We assume that a patient visit would result in generating a medical record that contains EHRs in the form of text-based information and optionally multimedia files. We also assume that for each patient visit, it's always guaranteed of generating text-based reports. Additionally, there is less than 10% probability of producing 1 to 10 image files and 1 to 4 video files. Further assumptions are made on the range of sizes for each generated data, as shown here. 1 to 4 megabyte image files, 10 to 50 megabyte video files, and 3 to 7 kilobyte text-based reports. This figure shows the sizes of cloud-based blocks that can be generated during a day under the established settings. In the figure, we compare our dynamic approach with two simple approaches, namely one block approach that stores all data generated by patients during a day in a single block, and two block approach that divides the generated patient's data into two blocks. The one block approach obviously produces the largest blocks, as all patient data generated within the day is crammed into a single block. The two block approach produces better results, as data generated within a day is divided into two blocks. The dynamic block approach produces a dynamic number of blocks per day based on the predicted number of daily patient visits. One block is created for every 200 additional patients predicted during that day. This means that only one block is created between a predicted patient visits of 1 to 200, 2 blocks for a predicted 201 and 400 patient visits, and so on. From the figure, we can see that we are able to keep a consistent block size of around 1 gigabyte with the cost of increased number of blocks per day when the number of patient visits are high, as shown by the increased number of dots as the patient visits are nearing to 1,000. However, we argue that this is well worth the trade-off, as the cloud-based blocks becomes much easier to maintain in the clouds and access by regular peers within the blockchain network when they are relatively manageable or small. The second case study involves testing the effectiveness of index links in searching for a particular patient's medical records containing their EHRs in a light blockchain. These experiments are designed to search for data stored in a simulated light blockchain that contains 10 years worth of information. For this experiment, we randomize the size of the hospital that each superpeer represents and the number of patient visits that each hospital will have based on their size. This is done to randomize the content and sizes of the simulated light blockchains. This figure shows the average search time for all EHRs of a random patient in respect to the number of the most recent years to be searched. Approaches that uses 4, 8, and 16 threads are simple sequential approach that searches for information in the blockchain block by block, hence sequential. From the figure, we can see that our index link based approach outperforms all the sequential search approaches for average search time. We can see the reduced effectiveness of using multiple threads in the sequential search approaches due to hardware limitations, such as the limited number of available CPU cores. In contrast, the index link-based approach only takes a few seconds to search for all relevant EHRs that belong to a patient. For our third case study, we record and analyze the retrieval time of multimedia files from a cloud-based blockchain. This retrieval time includes the time needed to extract multimedia files from a CBC, downloading them from the cloud to the end user's local machine, and decrypting the files to finally allow access to the end user. The table below shows the average number of blocks where multimedia files are found for a typical patient during a certain number of years based on our previous assumptions and settings. The max year section simply represents the amount of information generated within the specified time. The average number of blocks only include blocks with multimedia files and not blocks with text-based information only. The table also includes the upper range of the number of blocks with multimedia files that 95% patients are predicted to have. Finally, the average total size of multimedia files is also recorded on the table. Note that this number refers to the multimedia files present in the number of blocks presented in the upper range section, and not the average number section. The experiment figure shows that the average time needed to retrieve a varying amount of patients' multimedia files based on the number of blocks containing said files. We can see that from this figure that the extract time or the extract session is the lowest. This means that the process of extracting multimedia files from a cloud blocks component B in the cloud is quite trivial and short. The decoding process takes the second longest time due to the additional time needed to decrypt and decode more encrypted multimedia files. The download process takes the longest amount of time, which fortunately can be improved by having better network bandwidth. Overall, we can see that the typical worst case scenario, typical worst case of 20 blocks containing multimedia files takes around roughly 22 seconds, which is acceptable. For our fourth and final case study, we measured the performance of the consensus process based on the number of superpeer agents participating in the blockchain network. The timing of this consensus process begins when the primary superpeer agent verifies and digitally signs a new block in the initial verification phase, and ends after the primary superpeer agent sends the list of digital signatures to all other superpeer agents, as well as the regular peer agents in the notification phase. The timing does not include the amount of time used by other superpeer agents to notify their own respective regular peer agents to update their light blockchains. As shown by the figure, we test the consensus process using fixed block sizes of 0.5 GB, 1 GB, 1.5 GB, and 2 GB. We can see that the average consensus time increases faster for a new block with a larger size, and as the number of superpeers also increases. This is due to the additional time required to share a larger block with other participants in the blockchain network. Since each participant needs to download the new cloud-based block from the primary superpeer agent, increasing the number of superpeer agents or block size would inevitably lead to network congestion. This results in an overall longer time required to acquire the new blocks for all participating superpeer agents. Based on the experimental results, we can conclude that although our approach might not work well with a large number of superpeer agents, it demonstrates reasonable average consensus time average time for a limited number of superpeer agents of no more than around 30 agents. Conclusion. In this presentation, we have introduced a cloud-based blockchain along with a lightweight version called Light Blockchain as a novel approach to storing and sharing EHRs in a cross-hospital setting using the blockchain technology. The use of cloud-based blockchains to handle storage and sharing of big data allows regular peers such as doctors and patients to participate in the blockchain network via their light blockchains without the need for significant investment in network bandwidth and memory and storage space. The experimental results show that the cloud-based blockchain approach has reasonable performance for secure and reliable big data storage service designed for a healthcare system within a local area. However, there are several aspects of our approach that needs to be improved. In our approach, we assume that all superpeer agents can be trusted in the blockchain network, as they represent healthcare organizations. This can be reflected in our consensus process. However, we need to design a better consensus process that also takes malicious organizations into considerations. Our approach works best for only a small number of hospital participants, as shown by the case studies. We plan to improve our current approach by exploring the implementation of hierarchical architecture to allow for more hospitals to participate in our blockchain network overall. Finally, we plan to explore on a different domain, including smart contracts for real estates and electronic student records (ESR) management, with more and efficient and effective encryption procedures in our cloud-based blockchain approach. Such improvements would provide us with a more secure and reliable way to store and share sensitive big data in the clouds.